For a quick project overview, our project can be summarized as follows. It's a multi-purpose rover for industrial and construction use that picks up and delivers metal scraps such as nails, screws, paper clips, or if on a larger scale, larger metal bars like rebar, and can be controlled through Bluetooth signals, so it's completely hands-free, and it's small enough to reach hard-to-reach areas or dangerous areas that most humans wouldn't be able to reach. Our rover concept looks like this, with a dynamic drivetrain that's four wheels and has a two-motor drive, and a body that encloses all of our electronics, which includes our 12-volt battery pack, as well as our Arduino, and any other electronics that we have. Here is a high-level flowchart that shows our rover control system, which is split between Bluetooth control and things that are automatically on when we turn on the rover. As you can see, each of our control systems is connected through this flowchart. Now, for project features, our capstone can be broken down into these four following points. The first, as mentioned, is a two-motor drive drivetrain. The second is a Bluetooth connection for extended range and to be able to control the robot without having to use wires. The third is an electromagnet that's used to collect waste or metals. And the fourth is a capacitance circuit for our hazard lights. For physics applications, our two-motor drive drivetrain will cover circuits, including parallel and series, cover magnetic fields in DC motors, electric fields, current, and voltage across the motor. Our electromagnetic covers electromagnetic induction, properties of solenoid and permittivity constants, as well as energy storage in magnetic fields. And finally, our capacitance LED circuit covers RC circuits, capacitance, things like steady state, capacitor charging and discharging, as well as energy storage and capacitors.
In construction zones and factory areas, this rover can help with clearing hazards and other dangerous metallic objects. The rover can reach hard-to-reach and dangerous areas that people cannot. In addition, it mitigates human risk in construction work. This rover is also useful for environmental cleanup, where it can help with cleaning up metal waste.
CAD modeling was instrumental in the design of our build. Here's our robot leg structure. Here's all of our drivetrain parts. Here's our full drivetrain assembly. Here's our rover body that we use to house all of our electronics. And here's our full CAD modeled full body assembly. For materials used, we have an Arduino Mega as our main microcontroller. We have two 12-volt DC motors that we use for the drivetrain. We have an electromagnet. And finally, a Bluetooth module to talk to our phone.
For our drivetrain, we used a modified rear-wheel drive system with two motors controlling the back wheels, and we had the front two wheels on a free spinning axle. The rear motors delivered direct drive to the back wheels, which gave us efficient forward motion and also responsive turning through differential speed control. And we chose this configuration specifically because it provided us the best balance between power while also being easy to implement.
That's so sad. That's so tragic.
No, it's not. We
Wait, also, how can you?
Just so you know, I'm not helping you turn. I'm just holding the wheel.
Guys, I wrote this code. Guys, I wrote
Just so
this
you know,
code.
I'm not
Jonathan
helping you
Pan
turn.
wrote
I'm
this
just holding the
code.
wheel.
I didn't take physics.
I didn't take physics.
Wait.
The rover connects with the phone using the Apple software and the HC05 Bluetooth module. When the up button is pressed on the gamepad for the Dabble software, the rover moves forward, and when the down button is pressed, the rover moves backwards. When the left button is pressed, the wheels in the back turn in opposite directions, allowing the rover to turn left, and same goes when you press the right button, where the wheels turn in such a way that you can turn right. The RC circuit, as shown on the left, allows the LED to still have current going through, even when it is disconnected from the power source, which is the battery pack. This is because the capacitor is charged, so once you disconnect it, it will start discharging and the current will still go through the LED until the capacitor is completely out. However, when you don't have the RC circuit, the LED will just instantly turn on or off.
We analyzed the capacitance circuit for the LED, and we observed the current and voltage drops across resistors and or capacitors, and we did this for every stage of the circuit. So before the button is clicked, and right after the button is pressed, a while after the button is pressed, and after the button is off. Immediately after the button is turned on, the current will take the path of least resistance, which is the path with the capacitor, and it will completely ignore the 220 ohm resistor. And so with the R equivalence being 2000 ohms, the current would be 12 over 2000, which is 0.006 amperes, and the voltage drop would be only through the 2000 ohm resistor. A while after the button has been turned on, the capacitor will have reached steady state, and so current will no longer flow through there, and the new current would be 0.0045, which is obtained by accounting for the fixed voltage drop of the LED and the new REQ, which is 2220, which is just the two resistors in series. And so the voltage drop across the side with the resistor and LED would just be come out to around 3 volts, which means the voltage drop across the capacitor, which is in parallel, is also 3 volts. When the button turns off, the capacitor charged to 3 volts will discharge through the LED and 220 ohm resistor.
Since the Bluetooth HC05 module requires a 3.3 voltage on the RxD input port, we actually have to use a voltage divider to split the voltage into two halves. By taking a resistor that's 2 times as strong as the resistor on the other side of our circuit, we can actually split 2/3 of our current to go into the TX1 from the TX1 port to the RxD port, while the rest of the current goes back to ground. This makes it so that we can convert 5 volts of output into 3.3 volts of input for our Bluetooth module.
This is the standard circuit diagram of an L298N motor driver module. The E and A pin, in1 pin, and in2 pin control motor 1, while E and B pin, in3 pin, and in4 pin control motor 2. This allows the Arduino to control the motors directly using code.
These are all of the calculated and observed values for our solenoid electromagnet. As you can see, the length, diameter, radius, and the cross-sectional area were both determined or directly calculated with direct formulas from our ruler measurements. The loops inside of the electromagnet was calculated with a derived formula I'll be showing in the next slide, as well as the magnetic field of the electromagnet, which is also going to be shown from another derived formula from the next slide. And we know that the max current of our electromagnet is 0.46 amps, and the max lifting force of our electromagnet is 180 newtons. And both of these values are obtained from our specification sheet from the manufacturer we bought the electromagnet from. The magnetic energy stored in our inductor is 1 half Li squared, where W represents the magnetic energy, L represents the inductance, and I represents our current through the coil. We know that force from energy gradient pointing downwards is negative dF over dx, and when we integrate both sides from 0 to L and 0 to F, we get that the total force is equal to W times L, where L represents the total length of the solenoid. The next part of our proof looks at the inductance that is being represented in terms of the position x. We can look at the magnetic reluctance at each position x, which is the resistance to change in magnetic field, kind of similar to our value for L, except you take it to the power of n squared. This is useful later because we want to be able to isolate n. And our magnetic reluctance for the air gap is just going to be the length of this air gap, which is going to be represented by L g of x over mu naught over A, where A is the cross-sectional area of our electromagnet. Using our formula for our potential energy, we can actually simplify it to 1 half n squared I squared mu naught A over Lg of x. And since we know force is the derivative of our stored energy, we get negative WL, and our inductance can be used inside of the entirety of the formula. However, if you take the integral of this entire formula with a little bit of mathematical trickery, you can define our solenoid at negative L over 2 and positive L over 2, and you can kind of ignore the term at 0. This integral will evaluate to exactly 1 half n squared I squared mu naught of A over 1 over L squared. which is also equivalent to b squared a over 2 mu naught. As you see on this slide, the magnetic field strength versus current represents the graph we obtained from our data, representing a linear relationship between these two fields, also further solidifying the derivation you saw on the previous slides.
During testing, we noticed that when we turned the motor wheels, the L298N indicator lights as well as the Arduino indicator lights would turn on. This means that as the motor is being turned, there would be current going through.
This property shows the concept of electromagnetic induction. We can see an EMF is inducted through the changing magnetic field inside the DC motor, and that's what causes the LN298 to light up. The final constants that you see on the slide, mu naught, which is equal to 4 pi times 10 to the power of negative 7, mu of r, which is roughly 200, n squared, which is 4,859 squared, area, which is equal to 7.9 times 10 to the power of negative 4 meters squared, the length of the solenoid, 1.746 times 10 to the power of negative 2, and the formula that you see at the bottom were all used to calculate the inductance of our solenoid, which is equal to 268.48 henries. Note that this is an overestimation as there are edge effects in our solenoid, therefore resulting in the error you see.
We encountered a problem with the remote control not working with the Bluetooth. When the Bluetooth module is placed inside the plastic rover body, communication is significantly reduced, even though the non-conductive body of our rover is not a Faraday cage. We believe the plastic housing creates barriers that still scatter and absorb some of the 2.4 GHz radio frequency signals. Additionally, any internal metal components, such as wires, circuit boards, and motors, can create interference and reflection of the electromagnetic waves, reducing signal strength. We suspect, through trial and error, that the E&M wave gets disrupted into a different signal due to the magnetic fields produced by the other electrical components inside of our box.